Hello guys. In this video, I'm going to talk about vector field. So this is the first class in vector field, and I assume that you learned these topics already. So you should know the dot product and the cross product and lines and plane and line and plane equations are in space in vector and vector operations, and then you studied vector value functions, which means the calculus of vector value functions, the derivative, integral, and limit vector value functions. Also, how to describe a motion of an object in 3D, in the length of curve and curvature and normal vectors, and definitely you should know a TMB frame. So in also the you should know the functions of several variables, the partial derivative of the functions of several variables, and the directional derivative and the instant meaning, the gradient, and optimization problems, absolute maximum, minimum, and then the Lagrange multipliers. Finally, I believe you learned multiple integrals. Okay, so the vector field. So the vector field is a vector value function. So which means that the input is in the the coordinate in R2 or R3, and the output is a vector. So a vector field in R2, for example, is a function f that the function f is defined by the vector, and then each component, x component, y components are real value function, lowercase f and g. So lowercase f and g are functions, real value functions of two variables. So for example, if the vector field, a capital letter F, is defined by this, so x plus y comma 2x plus y, then the f of 1 comma 1. So I want to figure out the vector field at 1 comma 1. Then you simply plug in 1 into x and the another 1 into y. Okay, then here the real x component is a real value function f defined by x plus y, and then the second component is defined by 2x plus y, which is g. So f of 1 comma 1 going to be 2, and g of 1 comma 1 going to be 3. So what does that mean, 2 comma 3? Which means that this is the vector, which means whose starting point is 0 comma 0, and 2 comma 3 going to be terminal point. So 2 comma 3 give us the vector, which is a position vector, right? So not only the vector 2, we got 2 comma 3 at 1 comma 1 vector, we got for vector 2 and 2 comma 3 when you plug in 1 comma 1, but every single point on the R2 we can get the vector by that definition of vector field. So in physics, vector field establishes a flow of fluid and temperature and the molecules and the energy and so on. So in our world, the various occurrences can be visualized through vector field. For example, just the picture yourself seated by a window on an airplane, observing its wing. So, although unseen airflow over and beneath the wing, they concentrate on a specific spot adjacent to the wing, and then visualizing the air's movement there at the precise moment. Then this moment is defined by a velocity vector featuring three components, right? X, Y, Z. So, I mean, east, west, and north, west, and up and down directions. For example. So another nearby point by the wing at the same time experiences air movement at a distant pace at and course associated with its own unique velocity vector. So generally, at any given moment, each point surrounding the wing possesses a specific velocity vector. This assortment of velocity vectors, each assigned to individual point in space, forms a function termed a vector field. So that's the one of the specific example. And then um, so so see. Okay, so the vector field F, we put the arrow as the notation of the vector field and defined by like this. We haven't seen already, or you can express the vector field using the basis vector I and j. Okay, so let's see a couple of example. I mean more examples. So. Let's see. Vector field F is defined by this 0, comma x squared. Then what does this vector look like? Okay, I just want to visualize the vector field. So then we just pick the several x point because you know the y value is not involved in both x component and y component. So we just pick the several x components. For example, 1, 2, 3, 4, and then we can calculate the vector 0, comma x squared, right? So when x equals 1, the we got the 0, comma 1, and then when x equals 1, we're gonna get the 0, comma 2 squared, which is 4, right? So and then when x is I mean when y is fixed, okay, is 0, then when x is 1, 2, 3, 4, then we're gonna get these vectors. As you can see that x is increasing, then the length of vector is increase the quadratically. I mean, it's called exponentially, right? So, but the thing is this: since the value is not involved, as for each different y value, we're gonna get same the vector along that line, each line, you know. Okay, so it happens same in the other side when x is negative value. X is -1, -2, -4. Then we're gonna get these vectors increase as x is decreasing in quadratically. Okay, and then for each vertical line, we're gonna get the same vector as these vectors for each. Okay, so so the vector field of this the graph of the vector field of this one must be like this. And the uh, the thing is this, the other also I want to mention that then can you get the vector whose direction is the down? I don't think so because of x squared, because x squared is always positive. So now the for the second example, the vector field f is defined by x minus y comma x. In this case, then we pick the several kind of grid points. Okay, so 1 comma 0 and 2 comma 0 and 1 comma 1 and the 1 comma 2, okay, and so on. And then we can calculate the x minus y, which is x component of the vector field, and then x, which is the second component, or we can say y component of the vector field. Then you can see that you can figure out the direction of each the vector is you can figure out that it's the vector's direction is changed uh, the rotationally. Okay, so the other example is this: f of x comma y is defined by 2x comma 2y. So and then 2xi plus 2yj, you can say that, right? Because I and j are basis vector. I is 1 comma 0 basis vector on the x-axis, and j is the 0 comma 1 basis vector, which is on the y-axis. So then as x and y is increasing, then the length of the vector is increased. So then you see the red the vector whose color is red, red vector, you see that? As the point is getting away from the origin, then the length of the vector is increasing. You can see that. So then drawing the direction of the vector field from the origin, see the arrow colored by green. So these represent uh, the direction, direction of the most of the vectors, kind of the direction of vector in vector field in average. So these the vector these the line is called the flow curve or streamline. Okay, so where we can see this, and then what does that mean? Uh, the For example, let's say the particle is on here, and then as since the direction of the vector is outward, right? So we can say that this vector field represent the particles moving in the direction uh, the away from the origin. Okay, so for example, so here the particles move in the direction of the arrow with a speed equal to the length of the arrow. So as so considering this the ball, this one as a particle, then the particle is moving away from the origin, and then the speed of the object moving away from the origin is increased. Okay, and then second one, the vector field. Here's the observation of that example. So vector field are sometimes called the flow. Okay, so this because as you can see, we saw that the vector field in if consider this one is a particle, then that directions. This vector field represent the where which direction and how fast the particles are moving. So we can say that the vector field is kind of a flow. And then third observations. Continuous curves that are aligned with the vector field are called the flow curves or streamlined, as I explained, right? So in the example, there are a lot of examples of vector field: a radial vector field, a shear vector field, and channel field, and a rotation field. So let's see each one. The radial vector field in R2. So the radial vector field F is defined by R over this is the magnitude of the vector to the pth power. Okay, so and then we can rewrite this fraction as 1 over magnitude of the vector R to the p minus 1 power times vector r over magnitude of vector r. So what is r? R is here defined by just x comma y. And then now see, look at this second one. Look at this. The second fraction is the vector divided by the magnitude of the vector itself. So then that means that the magnitude of this fraction. Anyway, this is a vector, right? Still. And then the magnitude of this vector must be 1, which means that this is a unit vector. So this will only give us the direction of the vector, right? Direction of this vector field. And then the first term, since the vector is not involved, so the magnitude of this vector return just real number, right? So 1 over just a real number to the p minus 1's power is the real number. So this bracket just give us just magnitude. So now then let's try to visualize this vector field. So we pick the some grid point, okay, 1 comma 1 0 comma 1, and but you know what, since we saw that in here in this example the vector field was defined by 2 times x comma y, and the vector field was like this, right? So we expect that, we can expect that this one defined by just, x comma y, uh, this one or so, we can expect that, oh, okay, so the vector is a vector, a vector will be, the length of vector will be increased as the point is moving away from that origin. So yeah, that's right. So 1 comma 0, 2 comma 0, then there the vector must be like this, and then 0 comma 1, 0 comma 2, so and so on. You can see that the direction of vector and then the length of vector is increased. So but let's figure out specifically by number. Okay, for this case, when x is negative x comma y, or negative 1/2 for each, then we get the vector of negative 1/2 comma negative 1/2 divided by this is magnitude of this that vectors. Then we're gonna get square root 2 times this, right? So this is equal to then negative 1 over square root 2 comma negative 1 over square root 2. So and so since the what negative 1 over square root 2 comma negative 1 square root 2, this is in that third quadrant, right? And then so we can see that this vector whose color is red, that's the vector of that point. Excuse me. So now that's the vector, okay, of that at this point specifically, okay, under the definition of this vector field, which is defined by this. And then p equals, or so in this case we assume that p is 2. Okay. So now let's see. Now let's see p equals 2. Oh, sorry. So in this case, I just look at the example for p equals 1. Okay. Now let's see p equals 2. When p equals 2, the magnitude term will be changed. So magnitude is you see that bracket, and then 1 over the magnitude of the r to the p minus 1th power, right? So but here, since p equals 2, we're gonna get the just magnitude of the r, which is the square root of 1/4 plus 1/4. Okay, so but 1 over square root of 1/4, excuse me, plus 1/4 is the square root 2. Okay, so now then you see that p, since magnitude is increased in when p equals 1, the magnitude is square root 2, right? Now then in when p equals 2, we got the just 2. So which means that the length of the vector is twice uh, comparing with case p equals 1. So in general, the vector field should be like this. Okay, when p equals 2. Okay, so this is the is called the central forces. Okay, so which means the gravitational or electrostatic forces between masses or charges. Okay, so the gravitational forces or electrostatic forces between masses or charges are called the central forces. These are described by a radial vector field. Okay. So second one is a shear field. If F is the defined by 0, 8 times x to the nth power, and then a is a real number, n is an odd number. For example, a equals 1, n equals 1. Then, if depending on the sign of x, the direction of vector field is different, actually opposite. So we're gonna get this kind of the picture plot for that the vector field. Yeah, so why this is shear field? Because this side goes down, this side goes up. So we can is using this characteristic of the vector field, we can represent the shear force, a certain shear force, using that vector field. And the other one is this: vector field is defined by b times y to the nth power. So, and b is a real number. Okay, so you mean b equals 1, n equals 1, then see, we got this kind of figure. So when this side, the the points, directional points, gonna be this, and the other side, excuse me, bottom side is the direction of all the vectors, the the point out the left. Okay, so the last example is channel flow. So channel flow is defined by this a minus by square and then a minus bx square in the second component and the first component. So these represent the on that. Think about this. The if y value is bounded by the square root of a over b, okay, so that a minus b times y square is probably positive. You see that vectors in the inner in here point in the positive x directions. Okay, then the all the vectors in this vector field must be like this. Okay, so in that inverse, and then the other way, on the other hand, for this definition of the vector field, if a is bounded by negative square root a over b, and a square root of a over b positive square root a over b, then we see the direction of vector field represent the this. Okay, and then oh yeah, if there is this is I think the last one. Okay, so rotation field. Rotation field is the we just swap the x and y and then put the negative sign in either one. For example, here negative y comma x. Here's a y comma negative x. Then you see all the vectors, directional vectors indicate the rotation. In this case, the counterclockwise rotation. In this case, the clockwise rotation. Okay, please. So gravitational field and potential functions.